Now let's take a look at a specific example where we can use all the things we've been learning about. We're going to talk about something called free fall. Free fall is a situation where only the gravitational pull of the Earth is affecting the motion of an object. Imagine taking a ball and dropping it. From the moment you let go until it hits the ground or you catch it, that would be an example of free fall. But be careful, in free fall an object can actually be going up or down. If you throw a rock straight up, from the moment it leaves your hand until you catch it again, that's also free fall. Free fall doesn't mean the object is moving downward. It simply means that the only influence that's affecting the object's motion is the pull of the Earth. So objects in free fall can be going up or down. Now remember, anytime we solve a problem, we have to model the problem. We have to decide what things to include and what things to leave out. Free fall is a model that only includes the pull of the Earth. It does not include, for example, air resistance. Air resistance is certainly important in some cases, but including air resistance makes the problem a lot more complicated. And the truth is, in many important situations, air resistance is small enough that we can ignore it, and in that case we get the case of free fall. Now it turns out that when objects are in free fall, they move with a constant acceleration. We've just talked about how to calculate what happens in that case, and here is an example. In free fall, objects move with a constant acceleration. In fact, the acceleration is always downward. Even more so, it turns out that for a given planet, the acceleration is the same for all objects. So regardless of the size or shape of the object, if we can neglect air resistance, then all objects are going to accelerate downward at the very same rate. The value near the surface of the Earth is 9.8 meters per second squared. So that's the value that we'll be using in this class. If you go elsewhere, if you go to Mars, for example, it's about 5 meters per second squared. If you go to the surface of the Moon, it's about 1.7 meters per second squared. But here on Earth, it's about 9.8 meters per second squared. So now let's take a look at a specific example where we can apply this idea of a constant downward acceleration. Now, for purposes of this example, we're going to round 9.8 up to 10. So we're only going to do it for this example just so that the numbers are easier to work with. But again, anytime you're working a homework problem, exams, in class, whatever, we'll always use 9.8 meters per second squared. So here we have a person that's throwing a ball, and when the ball first breaks contact with their hand, it's moving upward at 30 meters per second. So the velocity of the ball is upward, but in free fall, and it's in free fall as soon as it breaks contact with the person's hand, the acceleration is the opposite direction, it's downward. So if the velocity is one direction but the acceleration is the opposite, as we've learned in this session, that means the object is slowing down. In fact, it's slowing down at 10 meters per second here on Earth. So if it's going 30 meters per second when the person releases it, 1 second later, it's going to be going 20 meters per second. 1 second later, it will slow from 20 to 10, and then after one more second, it will slow from 10 to 0. At that point, the velocity is 0. The object has stopped moving. It can't go any higher. So now, of course, it's going to start to move downward. Once the velocity is downward, the acceleration, as always, is downward. Now the velocity and the acceleration are in the same direction, and when the velocity and the acceleration are in the same direction, that means the object is going to be speeding up. And it's going to be speeding up at 10 meters per second per second. So 1 second after it reaches the high point, it's going to be going downward at 10 meters per second. The minus sign in the cartoon is for downward. Remember, when you're moving along a line, we can use plus and minus for directions. Oftentimes people choose up to be positive, so as it's going upward, the velocities are listed as positive. As it's coming down, the velocities are going to be listed as negative, the minus sign simply being a way of indicating the direction, downward in this case. 1 second after that, still speeding up at 10 meters per second, it'll be going 20. One more second later, it'll be going 30. If it's still airborne 1 second later, it'll be going 40. And as long as free fall is a good model, as long as it doesn't land, and as long as air resistance can be neglected, it's just going to continue to speed up at 10 meters per second per second. Now I would point out a few other things as you look at this cartoon, and these are always going to be true about objects in free fall. Notice that it takes the same amount of time to go all the way to the top that it does to come back to its original height. It takes 3 seconds to go up, and it takes 3 seconds to come back down to where it started. In free fall, objects always take the same amount of time to go up as they do to return to their original height. Also notice that at any given altitude, it's going the same speed in either direction. So when the ball is thrown, it's going 30 meters per second up. When it returns to that same level, it's going 30 meters per second down. But that's also true when it's at 20 meters per second. At that same height on the way down, it's going 20 meters per second again, only in the opposite direction. Free fall is always symmetric in these two ways. Equal times to go up and to come down, and at any given altitude, it'll be going the same speed in either direction.